Hello, Mr. Betts here. Let's take a look at an optimization problem. And this problem, we are going to be using our calculator. So we'll look at how we can use our calculator to help us with problems like this. So first step here is we want to look at what the model is going to look like, what the picture is going to look like for this problem. So we have two poles, one's 12 feet tall, one's 28 feet tall. They are standing straight up, 30 feet apart from each other. They're supported by wires attached to a single stake between them. We want to know where that stake should be placed to minimize the amount of wire that we have to use. We're going to give our answer as a distance from the 12-foot pole. So I'm going to keep that in mind when I'm setting up my model here. So we have a pole that's 12 feet tall. We have another pole that's 28 feet tall. We're going to assume that the ground is horizontal and there's 30 feet of distance between them. And we're going to have wires going from the top of each pole to a single stake in the ground. And we want to minimize the amount of wire that we're going to use. So to give a little bit more context here, since the answer I'm looking for is the distance from the 12-foot pole to the stake, I'm going to call that X. And then I could call this Y. I could introduce another variable here. However, I know that the total distance between the poles is 30, so I'm just going to right off the bat eliminate that variable and just call that 30 minus X. Now, what we're trying to do here is we're trying to minimize the length of the wires. So the wires are going to be the distances here and here. So I'm going to call those W1 and W2. So I'm going to say big W, that's the total amount of wire that we're going to use, is the length of the first wire plus the length of the second wire. Now, that's not really that helpful because we don't have much information in there. So what I want to do is write those lengths of wires as equations involving the information that was given in this problem. So using the Pythagorean theorem, we're going to have W1 is equal to the square root of x squared plus 12 squared. And W2 is going to be the square root of 28 squared plus 30 minus x squared. And for the purpose of just keeping things as simple as we can, I'm going to expand this and combine like terms and multiply out the 28 squared. So W2 is going to equal, so doing all of that, we're going to get x squared minus 60x. Then we're going to have a plus 900 and we're going to have a plus 784. So that's going to give us plus 1684. So plugging this and this for this and this, now I'm going to be able to write that equation for the length of the total length of the wire in terms of just a single variable x. And actually, let me back up here real quick. Since I have a variable x here, I want to make sure I know what kinds of values to expect here. I know x really could be 0, so we could put the stake right here at the base of the 12-foot pole. So x is going to be somewhere in the range from 0 to, if we put the stake all the way over here, x is going to be 30. I guess you could argue that we could put the stake on the outside. It does say that the stake is between them, but you could put the support stake over here. But if we start moving outside of the poles, then we're going to be using more and more wire. So going back to our equation, the total amount of wire we're going to use is going to be given by the square root of x squared plus 144, that's W1, plus the square root of x squared minus 60x plus 1684. Now, I know this is a calculator problem, and we're going to plug something into the calculator, but I can't do this yet. And it would be tempting to just graph this as a function in your calculator and look at where that's going to be the smallest. Our calculator even has the functionality to do that, so we can go in the calc menu and find a minimum. But in the end, we're going to have to justify our answer with calculus, and that is not going to allow us to do that. So the first thing I'm going to do here is actually take the derivative. So this is no different than what we've been doing with the other ones. Keep in mind that the square roots are this expression to the 1/2 power. So when we take the derivative, we're going to end up with something that looks like this. And with the chain rule, we're going to have to multiply by the derivative of the inside. And then same thing for this one. And then derivative of the inside is going to be 2x minus 60. And then just for the purpose of plugging into my calculator, I'm going to make this as simple as I can. And so with this derivative, I want to know where this derivative is either equal to 0 or is undefined. Well, it turns out that the denominators are never going to equal 0. So the inside of both of these square roots will always be positive, so we're never going to have a derivative that's undefined. We are going to have a derivative that's 0, but since it's a calculator problem, I don't have to try to solve this equation analytically. I do want to make sure that I write on my paper that we're setting this equal to 0, because remember, anytime we're using our calculator, we want to make sure that we write on our paper what we're doing in our calculator. So we're solving this equation here. I'm going to plug this expression into my calculator. I'm going to use the calculator to find zeros, and that's going to give us our critical values. So I've done all of that already. So I plugged the derivative in for y1. I changed my window to include x values from 0 to 30, because remember, x is not going to be outside of that range. And then I use zoom fit just to make sure we get a nice clean graph, and we get a graph that looks like this. Then I use the 0 function on my calculator to solve the equation where the derivative equals 0. So picking up at that point, I'm going to write on my paper, we have a critical value at, and this is a nice clean one here, x equals 9. Now it would be tempting to, at this point, just say, okay, well, that's our answer. Since x represented the distance from the 12-foot pole, that's going to be the minimum amount of wire. I need to justify, though, using calculus that that's going to give us a minimum. It is possible that at this critical value that we also have a maximum, or it could be a relative minimum, or it could be neither. So I'm going to make a sign chart here. So making a sign chart for W prime, that's going to go from 0 to 30. And our critical value is at 9. Now our sign chart here is super easy to make with what we have from our calculator. Remember, the graph that we have here is W prime, and W prime is negative from 0 to 9 and positive from 9 to 30, because we can see that it's below the x-axis to the left of 9 and above the x-axis to the right of 9. In fact, we don't even really need to make the sign chart because we have our graph here to justify it. So we're going to give our answer and we're going to justify. So we're going to say the minimum amount of wire will be when the stake is 9 feet. Don't forget to include units. So 9 feet from the 12-foot pole, because W prime is negative to the left of 9 and positive to the right of 9. So I gave my answer, but I also explained why that answer is giving us a global minimum. And we can use the first derivative test here, remember, for a global minimum, because the derivative is always negative to the left and it's always positive to the right. So the first derivative test has that special case where if there's only one sign change, it's not only a local minimum, but also a